Hi, everyone. Thank you for coming. So I'm going to tell you a little bit about the work that I've been doing with not just imaging spotted stars, but the things that I've been doing with those images and applying them and trying to get some science out of it. So when I talk about spots, I want you to first think about like a sunspot, because that's probably what comes to your mind anyway. So for stars other than the sun, we aren't able to resolve the surface in the same way that we can the sun. So this very detailed picture that you see here of sunspots, where you can see all the different features of it, the really dark umbra and the less dark penumbra around it against the photosphere, we can't really see that sort of contrast for individual spots on other stars. So when I talk about star spots, it's probably a better idea to visualize this whole sort of star spot group as a conglomeration, or sunspot group as a conglomeration. And that's, typically what we refer to when we talk about a star spot. So just to give you that idea so you can get a better picture of what I'm talking about in your head. We know that these are magnetic features. In the mid 20th century, Hale and Nicholson decided to put a slit across a sunspot, and they were able to see that there was splitting happening. You can see that here on the right. This was Zeeman splitting, which we know from atomic physics is due to a strong magnetic field. So this gave us the indication that these are magnetic phenomena. So one very basic idea of how a stellar magnetism could develop. This is not something that we definitively know at this point. So this is just a really basic picture to give you an idea of how these fields could be generated. This is a simple cross section of the star where we have the convective zone and the radiative zone, and where those meet in the tachocline. That's actually a layer of shear, and in that layer of shear, you start to develop a magnetic field. And over time, you build up your magnetic field because you have these small little magnetic regions, and they accumulate over time. And eventually, you can get this sort of idealized dipole view of the sun. But we know that it's not that simple. We know that the equatorial regions of the sun are rotating more rapidly than the polar regions, for example. This differential rotation, we know that the magnetic fields are also locked into the outer layers of the star. So because we have that differential rotation, the magnetic field is going to start getting dragged around the star. And so here's a cartoon illustrating that. And over time, that magnetic field is going to build up, and it's going to become so dense that in regions it's going to pop out of the surface. And so this little cartoon just illustrates that in the regions where the magnetic field is popped out of the surface, you are actually completely perpendicular or nearly perpendicular to the surface of the star, and you're not able to actually have your convection in those regions. So convection requires that you have a hot material rising, and it sort of gets, when it gets to the top, it sort of gets pushed to the side by the material behind it, and then ultimately it falls again as it cools. And so you can't have that sort of horizontal motion required from the convection when you have a strong magnetic field in place. So your material can't do that horizontal motion. So your stellar material can't efficiently radiate its energy in the same way that the rest of the photosphere can. So because it can't efficiently expend its energy, it's going to be cooler. And then because it's cooler, it's going to also appear darker. So that's how you get this big contrast between the sunspots and the photosphere. It's just this remarkable temperature difference. And in sunspots, it tends to be up to about 1,000 Kelvin. So I've now mentioned spots. These are just one type of magnetic phenomena. In the regions where you have the spots, I just already said that you have the magnetic field sticking out of the surface. And in those regions where it's sticking out of the surface, you can actually get a reconnection event happening. So here you can see a bunch of magnetic loops above the surface, above these active regions. And you've already seen it happen. When the magnetic fields reconnect, you have a flare, which expels a lot of photons out into space. And sometimes associated with the flares are coronal mass ejections. These are a similar phenomenon where the magnetic fields sort of reconnect and expel now charged particles out into the region, the sort of interstellar region within the solar system. So these are all fun things that can happen from stellar magnetism. but they also really do have an impact, particularly on the planets. And so we know that stellar activity can actually cause problems for planets with magnetospheres and atmospheres. It can, interact with the atmosphere and by stripping off the atmosphere, and it can also interact with the magnetosphere. We particularly know this because we know what happens when a coronal mass ejection hits our own magnetosphere. We get these beautiful aurorae. And so these become more dramatic when a coronal mass ejection has been expelled from the sun in the direction of the Earth. And we know that these things are related. So recently I've been doing some work. I just want to put the papers here if anyone happens to be interested in this sort of thing. I've been doing some work on understanding how the activity of the star can actually be impacting the atmospheres of the systems and whether or not they actually are able to sustain atmospheres. Another thing that the activity tends to have an impact on is actually our ability to detect the planets themselves. And so we know that stellar activity can actually cause radial velocity shifts. And to show that, I have this cute little cartoon from Rachael Haywood, where all the way on the left, she showed that just this nice little drawing of an absorption line that has no features in it, as well as a spotless surface. But then as soon as you put a spot on the surface, you start seeing that the absorption line gets to be distorted. And over time, as that spot rotates across the surface of the star, it actually causes a signature in the absorption line that mimics a radial velocity shift due to a planet. And so, so stellar activity can also give you a false positive on the detection of a planet. And I've been doing some work looking into this with Sam Cabot, who's a graduate student here at Yale, and we looked at a really spotted star to see if we could start understanding the impact of the activity on our ability to detect planets. Anyway, I spend most of my time doing imaging. So I want to tell you a little bit about that now that I've hopefully motivated you that these things are actually relevant to our lives, as well as our astronomical interests. Before I get into the imaging, of course, the type of stars that I really, really enjoy imaging are RSCVN stars. These are spotted stars, but they tend to be in binary systems with a primary star that's a giant and a companion that's usually a main sequence star. And they're really interesting systems because they're tidally locked in these really close orbits. So they have rotation periods on the order of they have orbital periods on the order of about 1 to 3 weeks. And they also are tidally locked. So that's their rotation period as well for the giant. And they also show lots of evidence of having a lot of activity in calcium H and K and H alpha emission. And so these things actually have these enormous spots because when compared to the sun, they have these really deep convective zones, and they're actually rotating relatively much faster than the sun is. So the same mechanisms that develop the magnetic field on the sun working on these stars that are much more extreme is going to cause these huge spots to appear on the surface. So these are really the most ideal type of star for doing imaging because it just has these giant spots on the surface that really make imaging techniques using the imaging techniques pretty straightforward. So I'm going to go through a couple of the different techniques that I use. The first one is with photometry. It's light curve inversion imaging. And so the idea here is that you have a light curve, and you can reconstruct the surface of the star that would create that. So you can see on the right an example of a light curve, and below that are the surface from 3 different phases. So you can see that when the light curve is at its brightest, this surface is almost entirely featureless. And so the idea is that we have an algorithm that breaks up the surface into individual patches and then varies those patches to get it to have a light curve that would match the observed light curve. So the great thing about this is that you can apply it to any star. If you have a light curve that shows rotational modulation, you can reconstruct a surface from that. We can constrain longitude pretty well, and it doesn't require too much data. Though I show it with a Kepler light curve here, we can do this with a much more sparse ground-based observation. We don't get very good constraints on latitude, particularly when we're using something like Kepler, which only has one bandpass. We're very reliant on understanding the limb darkening of the stars in order to be able to place relative spot latitude information on the surface. If we were to have more band passes, we would be able to do better in locating the spot in latitude. But when we talk about things like Kepler, it really is just some relative latitude information that we can get out, and that's just that's a known issue with the method. We also don't get any stellar parameters out. We have to put in estimates of the spot temperature and the photospheric temperature and those limb darkening coefficients, as well as the inclination of the star, to really be able to get an idea of what's going on the surface. So there's not really any information that we pull out in terms of stellar parameters. It's all stuff that has to go in. And we also aren't able to see anything that doesn't rotate in and out of view on the star. So if you have a spot, say at the pole, that doesn't go in and out of view, is just always constantly visible, we're not going to be able to see that with this method. So we're not able to get, the most accurate view of what's going on in the star in some cases.
Can I just ask a question about that?
Yeah, sure.
One question I have is, presumably you do need to know the rotation, the period of the star's rotation.
Mm-hmm.
And period is not a strict, it is a function of latitude.
Yes.
In most stars, and inclination in principle does have some imprint on the observable. Anyway, I just was I wanted to push a little bit on what you do have to know and what you can learn.
Yeah, so for the rotation period, typically we have a long enough light curve that we can get a good idea of what the fastest spot rotation is, because often in the stars that I'm looking at, there are multiple spots coming and going over time. And so you get multiple rotation periods and the signatures of that. So what we typically choose is the fastest period, because we assume that the star is probably rotating like the sun, because these are often, analogous to the sun, these stars. So we assume that the equatorial region is going to be rotating the fastest. So we assume that the fastest rotating spot is going to be the one closest to the equator. And that's really the best that we can do. We know on the sun, for example, spots don't actually form right on the equator. They form in these bands above and below the equator. But this is really the best that we can do. We can't assume any more than that, really. I am going to show some stuff I've been working on lately with differential rotation that maybe we'd be able to extrapolate to be able to find out more from that, but without really knowing exactly where the spots are on the surface, the best we can do is this, essentially. In terms of the inclination, especially when we do these reconstructions, there are some inclinations that just won't work for some stars, and that is an indication that what the surface is, we're trying to make an unphysical looking surface, and so that's an indication that maybe our inclination is too low usually. So we can get some very weak constraints, and I'm really kind of hesitant to even call them constraints. But yeah, so typically when I do these, I put in a range of inclinations and say, this is, what it looks like for these different inclinations. And if some of them look terrible and it looks like it's just making nonsense and it's not something that seems physically realistic, then we usually state that and then don't include images like that. So yeah, there is a lot that we don't know with this method, and we do have to make some assumptions, and I try to be as honest about that as possible and not to mislead people. So thank you for pointing that out further.
No, that answers my question really well. Thank you.
Okay, good. Okay, so so I do this a lot with Kepler. So Kepler has these beautiful 4-year-long light curves. This is just a 90-day stretch of that. And you can see here from peak to peak, things look like they're changing. And at some point, it looks like there's multiple spots. And so the idea is that I chop this up into individual rotations and I recreate the surface that would cause this. And they're all independent. They don't depend on what was previously imaged. For this method, there are other methods being developed that will have a dependence on that. But for what my purpose is, they're all independent and done individually of one another. So here's just an example of 10 of the surfaces that would be created from the star's light curve. Time progresses across the top row left to right, and then across the bottom row left to right. And so what you see here is an instance where there are two spots, and you can see that they're rotating with respect, rotating at different rates and sort of passing one another. You can also see, which is that differential rotation. So here, actually, the equatorial region is rotating more rapidly than the polar region. So that's why it looks like the bottom spot is sort of catching up and passing the top spot. You can also see some of the problems that we have with the method where we don't get enough latitude information. So when the spots are at the same longitude, the method just can't resolve them and they just look like one spot. And so it really just highlights some of the issues we have with it. So that's great. We have so much data, so I can make these fun little movies of the spots changing over time and coming and going and shifting. And this is a pseudo-Mercator plot, so it's the whole surface just flattened out. You can really see that for the grid that we do the reconstruction on, it has these bands of latitude that are just chopped up into different longitude chunks. And so you can see that the spots change over time. And this is fun to look at, but hopefully we can do some more science with this. And one thing that I've been really focusing on lately is it's going to be a common theme throughout this talk, is I've been obsessed with differential rotation, because I think I felt compelled to see if we had these images, can we actually reliably pull something out of them? And so the idea is to take two of these sequential images, and I'm going to cross-correlate them. So I'm going to break them up in those latitude bands, which are conveniently already there. And I'm going to cross-correlate them to see if we can measure the shift from one rotation to the next and how that depends on the latitude. And hopefully that'll be able to help us find some way to understand, find some way to measure the differential rotation of the star. And it turns out we were actually successful with this. So this is something that I spent all of quarantine doing, essentially, was working the kinks out of this. So the y-axis is the spin rate, so faster rotation is up, and then the x-axis is your latitude. And so we only look at the latitude above the equator because the algorithm doesn't have enough information from one single band pass to really put anything in the southern hemisphere. So we just only look up above the latitude or above the equator, because nothing's going to be nothing realistic is going to get plotted down there. So the thing to take away is that near the equator, we have faster equatorial rotation and we have slower, higher latitude rotation. So the dots with the lines through it are actually my measurements from that cross correlation. So it's discretized because the surface has these very discrete chunks of the sort of surface patches. The solid dark orange line going through it is the best fit that we found for it. And then the orange swatch is sort of our errors from doing some bootstrapping of the images themselves. So this was promising because we found a realistic differential rotation law for this star, which was exciting. I didn't make any slides of it, but we did do a whole bunch of simulations, which were really fun to do, of these idealized spots. And we did find that when one of those spots was on the equator and we knew the rotation period of the equator and the spot was elsewhere, we were able to actually get the differential rotation law that we assigned to the star out, which was really promising and really suggests that we can really start placing lower limits on the differential rotation that we're observing. So I thought that was quite exciting because we're getting this sort of two-dimensional information out of this one-dimensional observable of the light curve. So that's how I've spent most of my quarantine, was working on that, honestly. So I had to go into that rather lengthy divergence there. So another technique that I use is a Doppler imaging. And so this makes an image from watching the spots rotate in and out of view and how they affect the absorption line. So in this little image, in this little video here, you can see the spots are rotating and you can see the bump going through the absorption line is rotating with the spot. And the great thing about this is that we're now able to start constraining spot latitude. If you watch closely, you can see that highest latitude spot is really only affecting the absorption lines sort of near the core. But now coming into view, well, in a second, is an equatorial spot, and you'll see that that actually affects the absorption line all the way across it. So we're now able to get some information about where the spots are in latitude that we couldn't get as concretely in the with the light curve inversion. So we're able to get a better picture of what's going on the surface of the star with this technique. The problem, though, is that this is a bit more observationally expensive than photometric observations. It requires some pretty high signal to noise observations with high resolution spectra. We do require that we have pretty good phase coverage in order to make these images. And we also require that our stars be rotating pretty rapidly in order to be able to see the spot moving across the absorption line, to be able to know that the spot isn't evolving as it's doing that, and to be able to get some resolution to our image. So now we're starting to really narrow down the number of stars that we can actually apply this imaging technique to. And so I have conveniently some RSCVNs to show you, these stars with the really big spots on them. These are two of my favorites who will come up several times in this talk. This is Sigma Gem on the upper left and Zeta Andromeda on the lower right. These are again the pseudo-Mercator plots of the whole star at once, with the exception of the fact that the part of the star that you can't see due to inclination is just not plotted here. So these are really good images to illustrate that you have these bright and dark regions, and that the spots are really quite large on these stars. But the really interesting thing comes when you look at Zeta and you see that there's this polar spot. This is a spot on a part of the star that's not going to rotate in and out of view. So you can now see that with this more advanced technique, we're able to really start seeing something that we couldn't see with the light curve inversion. And I just have a few more images of Sigma Gem. These are from SONG observations. They're spectra from one of the nodes of SONG. These were over 4 sequential rotations. So all of these observations were taken over the series of about 80 days. We actually have 8 rotations worth where it's just observations straight through all of that. But I only show 4 of them here. And you can see that the surface is actually changing pretty quickly. So the rotation period of this is about 20 days. So in these 4 images that are 20 days apart each, a pretty significant change was happening. You can see evolution on the surface. This is work that was led by Heidi Korhonen at ESO. And we actually were able to measure the differential rotation on here. It's the same idea. We plotted them, how we plot our differential rotation is a little bit different, but the same idea with the rotation rate on the y-axis and the latitude on the x-axis. And again, we see the faster equatorial rotation and the slower higher latitude rotation. And I'm pretty excited about this result just because it was just accepted today. So that was some good news. And then the last technique that I want to show you is interferometric imaging, which is my favorite of these imaging techniques. So if you aren't familiar with interferometry, what it essentially is you have a bunch of separate telescopes that work together in unison to effectively make a much bigger telescope. So the idea is that you don't have to have this single behemoth dish in order to get a large telescope. You can have a bunch of little telescopes work together and be essentially a big telescope. So the diameter of our telescope is going to be equivalent to the distance between the 2 telescopes, or this baseline that I have on this plot or on this picture here. And so the idea is that your light comes into your star, or light comes in from your star and hits your telescope. And because your telescopes aren't on, your perfect telescope, you have these little pieces of telescopes that are on the ground. Your light has to travel different distances. And so you have to somehow make up for this different distance that the light has to travel. And we do that by having these movable delay lines, which are just mirrors on these carts that have like sub-micron precision in their location. So the idea is that your light gets emitted from your star at one point in time, hits your telescopes at different points in time, and then ultimately goes through some optics to end up hitting your detector all at once. which is a fun feature of optical interferometry that you don't need to do with radio interferometry. You can just collect your data and recorrelate it later and everything's fine. But in optical interferometry, you have to do it at the telescope at the moment, which is fun. So the great thing about interferometric imaging is that you can actually see the star as it is on the sky. There are no ambiguities of where the spots are located in latitude anymore. There's no lack of information of inclination or anything like that. How the star appears on the sky is exactly how you can image it, which is really fun. You can also see this. You can also continue to see smaller and smaller features if you have a bigger and bigger interferometer, which also tends to be a bit problematic because building bigger interferometers is a bit difficult. It's expensive. So we're really restricted to having stars that are large and bright. So we're dramatically cutting down the number of targets that we have that we're able to do these techniques on. But I think I hope to convince you that interferometric imaging is still pretty cool and we can get some really good things out of it for the stars that we can see. So I use the CHARA array, which is the Center for High Angular Resolution Astronomy array. It's 6 1-meter telescopes that effectively make a 330-meter telescope. They're located outside of Los Angeles at Mount Wilson. So the light comes in and hits your little 1-meter telescopes, which are all circled in the orange circles. Your light goes through some vacuum tubes, which you might be able to see. And then it goes into that sort of L-shaped building. And that's where we have those delay lines, that the mirrors on the carts that make the distance that the light has to travel all equal. And ultimately we hit our beam combiner. And the beam combiner I use here uses all 6 CHARA telescopes. It's the Michigan Infrared Combiner. It's now been upgraded through collaboration between the universities of Michigan and Exeter, and it's the Merck X instrument now. It works in H-band and J-band, and it has some brand new polarization capabilities. But yeah, so I haven't used the polarization yet, so I just use the H-band actually. And so that's the array that I use because it has the longest baseline. This is the largest baseline of an optical interferometer in the world at the moment. So here's the first images of a spotted star that were obtained with CHARA. This is work by Rob Parks. He took these sort of snapshots of Lambda Andromeda, which is another one of these RSCVNs. And you can see that he was able to see these big asymmetries on the surface and was able to see the spots. But what I wanted to do is I wanted to actually plot the data on the star in the same way that the Doppler imaging and the light curve inversion do, of doing the whole star at once. And so I actually used this algorithm called surfing or surface imaging that takes all of the data and plots it onto the surface at once. So the idea is that in a way that's analogous to Doppler imaging, each pixel and point on the surface refers back to multiple nights of data. So we're trying to get a more robust image of the surface of the star as opposed to these snapshots that are typical of interferometric imaging. There's just taking snapshots is a very popular way of doing imaging with interferometry. So this was really taking it to the next step of putting it all on the surface of the star. And so I'm going to take you back to my good friend Sigma Gem. This was one of the stars that I really wanted to image because it had these spots, and the Doppler imaging had always shown these big, nice spots. But the cool thing about interferometry is that you seem to always be able to find something you weren't looking for in your data. And so we actually were able to detect the companion in the data. So these stars have a brightness ratio in H-band of about 300 to 1, where the primary star is 300 times brighter than the secondary star. And so it was known to be a single line spectroscopic binary. So we weren't really expecting to find the companion, but behold, we found it. So the primary star is located in the center of this plot, the Sigma Gem A. That's the actual resolved size of the star on the sky. It's a little bit over 2 milliarc seconds in diameter. And the detections with the ellipses are just the location of the companion on those nights that we observed it. And those aren't the actual size of the companion. We weren't able to resolve the companion. It's just the detection's location. And so we realized that we found the companion, and this was great. So we went to our collaborators that had radial velocity observations, and we said, "Hey, we found it. Can you look and see what you can find?" And it turns out our collaborators were able to find the secondary in the radial velocity observation. So we have these beautiful visual detections, and we have this beautiful radial velocity curve. So we were able to get this glorious orbit out of the system. And so now I have the secondary on here. This is just an estimate based on the mass of the star, what its size would be, but we aren't able to resolve that with Chara. So that's its lovely orbit. And so now we really understand the system really well. So then we decided that, okay, now it was time to do the imaging because we understand what's going on in the system as well as possible. So we have this epoch of observations where we have simultaneous interferometry, spectroscopy, and photometry. And we independently imaged all of those techniques. So the first one is with light curve inversion. So this is from ground-based B and V photometry. This is an ATOF projection. So again, it's the whole star at once, just in a different shape now. And above the dashed line that you see at the top, that's the part of the star that we can't see due to inclination. So that's not visible. So everything sort of below that here is going to be what we're actually seeing on the star. And so this was cool. We saw this really simple two-spot structure on the surface. And this was exciting because were we seeing two spots that actually were at the same latitude, or was this just a demonstration of the problems that we have with light curve inversion of not being able to necessarily get the latitude information as accurately as we'd hope out? And it turns out that here's our Doppler image, and here's our interferometric image, and it looks like those two spots are actually at different latitudes and, as viewed by the other techniques, which is pretty great because we're really showing one of the problems with the light curve inversion method. And there's also this higher latitude stuff that we see in the Doppler imaging that we don't see in the light curve inversion, and we maybe see something of in the interferometry, but we're not sure. We hesitate to say whether it's there or not because we actually don't have good phase coverage on that side of the star with the interferometry. We had one night of observation, and that's not necessarily going to get us the resolution that we want on that side of the star. So we decided that we wanted to take another look at the star again a year later, and I will get to that in a second. But first, showing these images is great. Showing this comparison of the temperature plots is a nice qualitative thing to do, but we wanted to do something more quantitative. So we took each of these surfaces and we made the V-band light curve that each of these surfaces would create. And this is what we got. So again, with the photometry on the bottom row, the Doppler imaging and the interferometric imaging, the red dashed lines are the light curves created from those images that we made. So on the bottom row, we have the light curve inversion, and that's fantastic that it matches the photometry so well since that was its input. The great thing about the Doppler imaging and the interferometry is that you see that it has the same shape to the light curve, but the amplitude is a bit different. And this amplitude difference is actually something that we see with some frequency in Doppler imaging, in that the observed light curve has a higher amplitude than the sort of reconstructed light curve from the surface. And this could be from the fact that when you do Doppler imaging, you're only using like 4 absorption lines. And so you might not be getting the full picture of the surface of this that you would be getting in sort of the whole disk integrated flux sort of way that you get with photometry. So that could be leading to that problem there. Yeah, so we realized that we wanted to have better phase coverage with the interferometry. So we did this again the next year, and the star had changed significantly, which was kind of fun. Again, this is an ATOF projection, so the spot that you see on the left and on the right is actually the same spot. And we saw that things continued to be complicated in the other imaging methods as well. So we have all these these sort of equatorial spots. You might notice that there are more spots in the equatorial region in the interferometry than in the light curve inversion. And that's not shocking because the light curve inversion, when the surface gets very busy, has a hard time resolving the features. So that could just be another, result of the imaging method. We also, now we see these high latitude regions on Sigma Gemma with both the Doppler imaging and the interferometry, which is fun. We did the same thing where we reconstructed the light curve from our images, and you can see that it's a bit alarming that the Doppler image light curve has a significantly different shape than the other two. It's not just the amplitude at this point, it's also a difference in shape. And we think that the more complicated the surface gets, the more difficult these different methods are going to, the more difficulties these different methods are going to have with the imaging. So we weren't too disheartened by it, but we had hoped that they had matched up a little bit better. But just for fun, here are the two images from the interferometric observations in H-band as they appeared on the sky. Just rotating. I never get sick of looking at these, so I have to show them. So sorry about that. So what I want to tell you about next is what I've been working on currently, because these images are a bit old at this point. So I actually have a recent data set from last November through this February, where we have interferometric observations in November that are simultaneous with Zeeman Doppler imaging spectroscopy. And so the difference between Zeeman Doppler imaging and Doppler imaging is that with Zeeman Doppler imaging, you have polarimetric data. And so you're able to actually get an idea of what the magnetic field looks like with those observations. And sort of so we can really see what the structure of the magnetic field is, as opposed to just comparing what the spots look like on the surface. We're going to be comparing what the spots look like with the interferometric imaging, and what kind of magnetic field structure we're seeing with the Zeeman Doppler imaging. And this is particularly interesting because we have 4 months of the Zeeman Doppler imaging observations. They span until February because we wanted to overlap with TESS. So we have the simultaneous TESS observations in late January, I believe. And unfortunately, Chara is not good. It's not good to observe a Chara in January. There's usually snow and clouds, and it's not a very pleasant time to try to observe. So we pushed the interferometric observations a little bit early, and we have the constant observations in spectroscopy. So hopefully, we'll be able to see any evolution. We'll be able to understand how it evolved from the time we have the interferometry to when we get to the TESS observations, which we sort of threw in for extra fun. I'm also working on differential rotation. I really mean it when I said that I've been obsessed with this. So I actually got three data sets of observations of Zeta Andromeda, which was the one I showed you with the Doppler imaging with the polar spot. Here it is, and 2 years later. And so we have these observations, and they're beautiful. We wanted to be able to say something about how the spots change over time. And so I had this idea to observe the star over the course of 6 rotations. I think it was 6. And so I have 3 images that are spaced by like 1.5 rotations in between each. And at one point we're overlapping with TESS observations, and through all of it we have spectra. So we can again see the evolution of the spots. And so the idea is that hopefully the spots will have moved with respect to one another significantly by the end of our observation. So we'll be able to do the first study of differential rotation with interferometry, which is exciting. We'll be able to actually see how these things are moving with respect to one another on a star that's not the sun. We might also be able to see some evolution of the spots, which is always exciting as well. And that's Zeta and as it was in 2013, just for fun. And so then these are great. These stars are all fun, and the big spots are really exciting to image. But I also have been wanting to push this further and observe main sequence stars to see if we can get an idea of if we can actually image the spots on these stars. And so we've been looking at Epsilon Eridani, which is, I think it's like a K2 star. It's a main sequence star, and it's a little bit cooler than the sun. And it is known to have spots. This is what the spots looked like with most observations a few years ago. And it turns out the spots on this star are actually big enough to be imaged with interferometry. So we have been working on getting some data from our MERC-X instrument, and we are also getting simultaneous express spectra. And express is the extreme precision radial velocity instrument that Deborah Fisher here at Yale built for the Lowell Discovery Telescope. And so we've been trying to get simultaneous observations with that. And we have a data set from November where we see that at one point in time, the interferometry doesn't show any indication of spots. And we have spectra from that night. And then a few days later, we do have indication of spots in the interferometry. So we believe that we should be able to get an idea of what the spectrum of the star looks like when it's unspotted, and hopefully we'll be able to separate that out from any residuals of the spotted star, of the spots, and get an idea of what of how to move forward in order to be able to use that information to separate stellar activity and planets. And the really cool thing about this is that there's a new instrument coming to Chara in 2022. It's called Spica. It works in visible light, and it uses all 6 telescopes from Chara. So MERC-X is great, but it's in infrared. So moving into the visible wavelengths will improve our resolution. So we'll be able to see smaller features on the stars that we've been observing. And we'll also be able to resolve features on stars that are smaller than the ones that we've been looking at. So I tend to look at stars that are like a milliarc second, or about 2 milliarc seconds on the sky, which is quite small. And there aren't that many stars. So this will really open up the number of targets that we have available. And the really great thing about moving into the visible wavelengths is that we're now going to be able to have a better contrast between our spots and our photosphere. The spots are going to be more prominent against the photosphere in this wavelength. So there are all sorts of benefits of moving to the visible wavelengths with this. Yeah. So all of this together, it's great to just image individual stars and learn everything I can about an individual star. And I think that's fun, but I'm also really wondering if we can do some larger scale studies of these things. So another thing that I'm working on right now is imaging photometric archives. And so the idea is that I'm taking the Kepler archive and I'm imaging the many thousands of active stars in it. So if a star has a 4-year-long light curve and shows an indication of having evolving spots on it, in the next few months it will be imaged with the light curve inversion. And so the idea is that I'm going to have all of these surfaces, and I'm going to be able to do all of these studies on it to track the spots over time, do the differential rotation studies, and the hope is that I'm going to be able to determine some common star spot characteristics. The goal is to be able to be able to say, I have a star of a particular spectral type, and I expect it to have this sort of spot on it. I expect it to have spots that last this long, or be covered by this amount of spots. Like the goal is to be able to say something interesting about a whole class of stars, or to find out that no star is the same and everything is doing its own strange thing. Either way, it's interesting. So hopefully we can get some good results out of that soon. That's what I'm going to be working on. I think I've hit my limit of the tools that I want to develop for this technique. So I just really need to get the images to be completed and have a whole set of them so I can start doing some big analyses. And so, I already mentioned differential rotation, that this will be fun for that. We're going to be able to get some cool ideas of what's going on the surface of different classes of stars. I'm also going to be looking into active longitudes, which are a really fun thing, where spots seem to continuously form and disappear at the same longitudes repeatedly. There are lots of ideas of how this could happen. It could be a companion that's tied to the rotation, and there's a magnetic connection between them, and that's what's causing it. I found a really interesting star that is a binary system, where there are 2 of these active regions, and they have different rotation rates, so they're at different latitudes, and so they rotate with respect to one another. So I really want to find out if these are a particular class of star, if they have to have companions, what sort of thing I can find out about that. And then I want to investigate stellar flares a bit more. So I showed you that cool video at the beginning of the brightening of the star. This is something that happens on a lot of spotted stars. It's not just the sun. And I'm interested in looking to see if, like on the sun, there's a correlation between the spots and the flares. I did a paper that it showed there's an indication of that, but other papers have shown that at different classes of stars, it doesn't seem to show that indication. So I'm really interested in knowing if I have this huge, large-scale study of stellar activity, can we definitively say something about that? Yeah, so then the last thing that I hope to do is really to start making connections between stellar activity and planets more. And I've already been doing a little bit of work on that, but I'm hoping that if we can get a good understanding of what is happening with these different stars, if we can really start pinning down what types of stars have what kind of spots, maybe we can start making model spectra that have spots in them so we can compare to observations to see, what kind of scale we expect a star spot to, what kind of scale of an effect on a radial velocity curve we expect a spot to have a particular kind, not just based on, hopeful theory of what we think we know, but based on what kind of spots these stars actually have in a more realistic way. And so I'm just going to wrap up here that I have all these lofty hopes for trying to apply all of these image results to different areas of astronomy and really get an understanding of what's going on in the stars. And I really think that imaging is going to be a really exciting way to get there. And in particular, I think interferometric imaging is the way forward. I'm always going to be an advocate for that. So hopefully we can start getting some results when we get finer detail on these stars, and when we start observing more of them, we can really start getting an understanding of what's happening and making connections with broader theories, and really hopefully helping find smaller planets that we aren't able to find now, and really start disentangling signatures, because a lot of people are starting to see the importance of understanding what's happening on the surface of stars with detecting planets. And so I'm hopeful that my work can help contribute to that. So I thank you very much for your time.
Thanks so much, Rachel.
Thank you.
Yeah, so please, if you have a question, go ahead and raise your hand in the chat. I see that Hog has his hands up. Go ahead, Hog.
We've talked about this offline, so you can predict what I'm going to ask. And at the end, you said, that from these understanding, from the sort of statistical understanding of these target stars, you can understand what are going to be the imprints on extreme precision radial velocity measurements for finding planets. But I'm interested in the question of whether, if we really want to find Earth-like planets, maybe we really need to model in detail every aspect of the stars that we're observing. And maybe there's a prospect for EPRV projects to actually have a continuous integrated real-time model of the stellar surface. Do you think that's A, possible, and B, would it be helpful? This really matters for projects like Express and Terra Hunting.
Yeah, I think there are multiple ways we need to go about trying to figure this out. I don't want to put all of our eggs in one basket, so to speak. I think having multiple different ways of going about this is going to be a good idea. And I am intrigued to find if my interest in doing this really comes from the stars themselves, honestly. And so I'm interested in finding, is there some understanding that we can find of do stars all have totally different spot configurations, or is there some similarity? So I'm invested in doing that pretty much based on my interest in the stars, but I do think it does have some impact on the planet, detecting the planets as well. But I do agree with you that having the continuous monitoring of the stars is really going to be the way forward. I don't know how practical it is, because I'm going to say that the interferometric monitoring is going to be the way to do it, because it's the only way to definitively see what's going on the surface. And I think we need that in order to be able to really disentangle the signature of the radial velocity. And I know that's not what anyone wants to hear, because no one really ever wants to hear that they need interferometry, but I think it's necessary for this.
But imagine the really optimistic future that all astronomers, well, this is pessimistic for you, but imagine the optimistic future that people are willing to put arbitrary resources into EPRV. Would it be possible to take interferometric observations on with the same kind of cadence that Express can take radial velocities, or is there just no hope of that?
Yeah, if you have a dedicated instrument for it, you can. So when I observe, I spend entire nights on one star, and I observe it as many nights as they will give me for an entire rotation, which is probably overkill in some respects, but I don't think it is, because the more data you have, the better the image you're going to get. So, if it's realistic to have, several interferometers doing this, it's probably the way to go. You can, so each data set for interferometry takes about between an hour and an hour and a half to obtain for this instrument. And so if you could probably get away with doing, every other night and shifting through different targets. So you could probably, if you had like a set of 10 targets or so that you really wanted to do this with, I think that would probably be the way to go if you had your dedicated interferometer for it. So this is really lofty, hopeful things.
Yeah, but I mean, I agree. But if you think of the scale of NASA's investment in exoplanets, it's not inconceivable that we could be thinking in those terms.
It's not, because a large interferometer is going to be cheaper than a 30-meter telescope.
Exactly.
Yeah. So ideally this would happen, but remains to be seen if we can convince people of it. And so I think I think the project that I'm working on with Epsardani is going to be a good step forward in being able to show that we really can do this and that it is important to do it. So hopefully we'll have success with that project, and I will have results soon. But we'll see. But I definitely think that this is going to be the most helpful way we can do it. And I'm sure the statistical methods are also, I definitely agree that statistical methods of trying to separate out the noise from the spots from the planets is also an essential way to go to this problem. I'm just biased because I like my imaging, honestly.
Okay, David has his hand up. David?
Yeah, so thanks for a very nice talk. What do we know about, well, with the sun, we have this 11-year sunspot cycle.
Mm-hmm.
What do we know about the cycle of activities on other stars? And when they're less active, is the radial velocity data cleaner?
So we do know that other stars do have cycles, and we do know that they are on different time lengths than ours. We have the Mount Wilson had an activity survey for like 30 years, and there were a bunch of activity cycles detected in that. Some activity cycles have been detected in Kepler data, so even shorter scale activity cycles. In terms of the radial velocity, I don't know 100% for sure, but I do believe that when the spots are smaller in activity minimum, they're going to have a smaller impact on the radial velocity. And if that's wrong and someone else here knows definitively and can contradict me, I welcome.
Yeah, I mean, I wonder, because it would suggest there's sort of an optimal time for observing a particular star.
Yeah,
right?
I would think when the spots aren't there is definitely when we want to try to be observing them, for sure.
If we knew when all the, that's a cheaper program than David's of having interferometers on everything. Just monitoring with a small telescope potential target stars in advance, knowing when they're less active and knowing when to go after them might be a more plausible, lower cost alternative.
Yeah, I agree, but you get the activity cycle from years of monitoring. So in terms, so it's also observationally expensive in that way as well. So I think we're finding that there's no real easy, fast way to do this. That's going to be an investment of time and or money.
Well, is Rubin good enough to do that monitoring? Right, we'll have lots and lots of data soon.
Photometrically, yeah, I think the cadence is going to be pretty good for this. I can't say more. I need to look into it further, but I do think that it's going to be a promising resource for helping with this.
One real problem though is that Rubin has extremely bad bright limits, and we work
Good point.
so bright that, I mean, of course, you know, clever people on Rubin will figure out how to photometer the bright things, but really it saturates all of our interesting targets, and all of Rachel's, I think, saturate.
Yeah,
everything.
Mine are all naked eye targets.
Yeah, exactly. So the other thing I would say in defense of my position is that it would be really fun to have dedicated interferometers working on all the G stars.
If you could build one, I would happily help you run that. I think that would be so exciting.
A cool thing to do. I wonder whether Rubin can do bright stars better than we think, because you can, you know, if the central particles are saturated, you go further out.
Yeah, I bet it can. It's a really interesting project that that's a good thing that we should think about when Rubin starts up.
Okay.
The bright limit is ridiculous.
If you have any last questions for Rachel, please put your hand up now while I'm asking my question. Rachel, is there any chance that with TESS we could get light curves of M dwarfs either side of the fully convective boundary and say something about the differential rotation? Or maybe it's crazy, maybe they're just too faint. I don't know if you've thought about that at all.
So I tend to steer away from the fully convective M dwarfs because their light curves are often in two classes. One is where the spots don't change very much over long periods of time. And one is where the spots change very rapidly, such that they're not coherent from one rotation to the next. Like they're changing that rapidly. So I tend to stay away from those ones.
I see. Okay.
But if you can find some that have more stable spots that are more slowly evolving, such that they stay put for like maybe 2 or 3 rotation periods, then yes, we can absolutely try to do something with TESS.
Okay.
But if it's observable with TESS in like a normal sector that's only 29 days, it's going to have a pretty fast rotation, and that's probably going to be a more active star.
Mm-hmm.
So we'd have to look at the overlap regions, the CVC.
Okay, cool. I don't see any more hands up in the chat, and we're also out of time, so that works out. Thanks everybody for coming to this talk. Let's thank Rachel again.
Thank you.